politically,
Kind of looks
this
like a
is a disturbing
motivational
image,
speaker, like a
whatever.
Tony
That's
Robbins.
all we
Doesn't it
wanted to
look
cover
like Tony
in this video.
Robbins?
See you in the next video. Hello, everybody. Welcome to OpenCV weekly webinar. And today I'm going to present a tutorial on seamless cloning. Before we do that, I want to present my other host, Phil Nelson, who is the Director of Content and Creative at OpenCV. Phil.
Yes, that's right. It is me, the co-host with the co-most, the second banana who is second to none, your plus one and only, Phil Nelson, here to remind you of a few things we do every single week here on OpenCV Weekly Webinar, one of which is a special giveaway to one lucky viewer in our Zoom audience. If you're not in our Zoom chat, you can get there by going to opencv.live. Right now, you've got plenty of time to get in before we do our giveaway at the end of the show. I will be asking a trivia question that one of you will answer and win an OpenCV course of your choosing. We're also doing Q&A from you in the audience, so at any point in the Zoom chat, use that little Q&A button to ask a question and we'll do our best to flow it into conversation. Or if you're watching elsewhere, type your question as a comment in the comment section. We'll do our best to get to as many as we can. Back to you, Satya.
All right, and the viewers of this webinar today will also get a chance to buy OpenCV courses for a discount. I just have a coupon for 5 people, so we will, during the webinar, I'm going to share the coupon code in case people are interested. And the reason we are doing this coupon code thing is that this material, because this was very, very last minute, I literally stole it from the course and I'm presenting it. So you will get a sense of what kind of material we present in the courses. And this seamless cloning, for example, it is a very simple concept, but if you go and read the paper, it's going to look very intimidating, right? And our job at OpenCV courses is to simplify things and present it in a way that everybody can understand. You don't need to understand all the math, but you need to understand the concept. And that's the biggest thing. So hopefully, this thing will be very illuminating to people, even who know seamless cloning or techniques like this.
Plus,
so let's
knowledge wants to be free, man.
Yes. All right. So the host has disabled screen sharing. Wow.
Oh wow, I am the captain now. Hang on, I'm fixing it.
All right.
All right, you're up.
Okay, thank you. And I'm going to share. So the way this thing is, we are going to do it is we are going to first present the theory. And I'll simplify the theory so that it's not intimidating, because if you read the paper for seamless cloning, it will, be intimidating. You will be talking about, image integration with Dirichlet boundary conditions and God knows what. But for this purpose, I'm going to simplify it quite a lot so that you understand the concept. Now, to begin the thing, what is seamless cloning? This is an example of a destination image. You can see that it is, an evening sky. It has this yellow hue that comes in the evening. And I have this source image where I want to actually insert this airplane into the sky. And I want to make sure that, it doesn't look bad. It looks natural. It looks like the lighting is preserved and things like that. So let's see a naive cloning example, right? You took that airplane and simply pasted it on this picture. It's
nailed it. No notes. Bad. Perfect.
Right. So unless you are the parent of the person who did this, you will not be impressed. So now you could actually mask out, right? That cloning, one slightly better technique would be to mask out the background using Photoshop, etc. And then you try to put it in, and it looks funny because, the evening sky, the colors of the evening sky, they are not reflected onto the airplane. So it doesn't look right. What we really want is something like this. From the first picture, we want to go to this picture where it becomes part of the environment, right? The airplane looks like it is part of the same environment. At the same time, the features and the colors of the airplane are also preserved, right? So that's what we are going to learn how to do this in using OpenCV. Now, the basic idea behind seamless cloning is that we have to copy the gradients from one image to the other instead of copying the pixel intensities. And this will be very clear to you after you see the 1D case, right? Let's look at an example. So before we go to the example, let's even understand what derivative means, right? What differentiation means. If you remember from calculus, high school calculus, we know about integration and differentiation. Integration, if you think about integration in discrete domain, integration is nothing but summing up values. And differentiation is differencing values or subtracting values. And we'll see an example here. So let's say you have a curve like this, yx, and the derivative of this curve in 1D is basically you sample the curve, and then you take the differences of two nearest neighbors, right? You, at any point, you do x plus 1, you find the value of y at x plus 1, and you subtract it from its nearest neighbor. This is, this is not symmetric differentiation. You could also go, x plus 1 and minus x, y x minus 1 divided by 2. That would be central differencing. But this is the basic idea that you're taking small differences between corresponding, you take a small step and find the difference between that. So that's essentially differentiation in 1D. And you can see that this was the original curve. If you plot this curve, which is, the derivative of this curve, you will find, you will get this curve, right? Any questions about this? Did people totally get what 1D derivative in 1D looks like?
Seems like so far so good. Just a quick reminder to folks that are joining us a little bit late. Today's episode is not about CVAT. We'll be talking about that a little bit, maybe down the road a piece. Today we're giving you a tutorial. We hope you enjoy it.
Yeah, sorry about that. This is a last minute change. We could not make the CVAT episode happen, but it will happen in a few weeks. So and people who are joining in late, this episode is about seamless cloning using OpenCV. So this is a tutorial that we are going through. And until now, we have covered very little. We have just come up with the derivative of a 1D function. And we'll see how that translates to, how we can use it for seamless cloning. So this is a function, okay? And so just to give you a numerical example, let's say we have this 1D curve, which has these values 5, 7, 10, 12, 7, 2 along the x-axis. The y values are 5, 7, and these are equally spaced. Now, if you take the derivative of this curve, you basically take the difference. So 7 minus 5 is 2, 10 minus 7 is 3, 12 minus 10 is 2, and 7 minus 12 is minus 5, and so on and so forth. So that's how you get the curve, right? It's pretty straightforward. Now, what does integration look like? Integration is basically adding values successively in the discrete domain, right? When you're talking about discrete values, you simply keep adding the values in the curve. And this is what it looks like. The integral is shown in the bottom line. And we keep adding these values, 3 plus 2 is 5, 7 plus 2, 5 plus 2 is 7, and so on and so forth. So this is the curve we get for integration. Now, there's a problem when we started with the curve. This is not the curve we got when we started, right? We had started with a different curve. Let me show you what the curve looked like. The curve was started with 5, and here the after integration, we actually did not get the curve 5, right? You can see that there's a difference. We got 0, and the original curve had 5 in that place. But I mean, from high school, you know that two different functions which are off by a constant will produce the same derivative. And that's exactly what is happening. So we need to fix this integral with a constant value. If you add 5 to all these values, we get the original function back. So you can see that all these values are off by 5. So that's, we need one example when you want to get the real integral. You need one value on the curve, and that will fix the integral for 1D. Is this clear until now, how integration and differentiation works in 1D?
It's about as clear as it's going to be to this high school dropout.
All right. All right. So that's good. We have one data point who is
yeah.
to go after. So, okay. So this is in 1D. Now let's look at some example of seamless cloning in 1D. Let's say we have two curves, the blue curve and the orange curve, and we want to seamlessly clone, seamlessly join the two curves, right? Now, what I mean by that is we want the left part to come from the blue curve and the right part to come from the orange curve. So if you actually just join the two things, this is what the curve would look like. That the left is from one piece and the right is from a different piece. And there is this very sharp discontinuity between the two. So what we really want in seamless cloning is the left part came from this curve, but then it continued from the right part continued from where it left, not this very sharp discontinuity. So how do we do that? Let's actually, this is just showing that this piece of the curve has come from that side, but it started where the old curve left. So we can do this cloning in gradient domain. Let's see how it is done. So both these curves, we have Bx and Rx for blue and red curve. We take the derivative of the two curves. And as you had seen, this is what the derivative would look like. We are taking successive differences. And instead of joining the original, we are joining the derivatives, right? So this is the line at which we are finding, we want to clone. So we will actually, just so people remember, we wanted to clone at the number 50 point. So this is the point 50, and we wanted to clone at this point. So going back to this curve at 50, we are joining the derivatives, right? We are joining the derivative curves instead of the original curve. So once we do that, it's going to look like this. But then we integrate this derivative, and here you go. You actually get back the original curve, the curve that we want. When you integrate this curve, you actually get this green curve, which looks like seamlessly cloned, right? We wanted it to start at this point and not at some other point. Is this example clear until now?
Yeah, that seems like people are getting it. It also looks cool.
Right. So the idea, now when you extend this idea to 2D, it's the same idea. The 2D example also works in a very similar way. And this I'm just showing the original. When you do it in the intensity domain, you get this sharp discontinuity. But if you do it in the derivative domain, you do the joining in the derivative domain followed by integration, you get this smooth transition. So in 2D, in 1D, we just had one dimension. We could just take the derivative in one dimension. But in 2D, we have two derivatives. We have the x derivative and we have the y derivative, right? So we have to, and in 1D, when we are doing the integration, we need 1 point on the curve to fix the integral, because the integral could be off by some amount, right? In our example, the integral was off by 5. And if we just knew 1 point, we could figure out what was the delta and add it to the curve so that the whole curve was shifted by 5 and we got the original curve back. In 2D, we need boundary conditions. So when we integrate in 2D, we need to know an entire curve or closed curve along the boundary for this integral, for fixing this integral, right? And here's where we make a little jump where we don't go into the math in detail. In 2D, what integration means is, we can set up this thing as a Poisson equation with Dirichlet boundary condition, which basically says at the boundary, you know the values, and you need to solve something called a Poisson equation, which we will not go into, but you can imagine that this is a kind of integration. You're taking these values and then solving this problem iteratively, and from the derivatives, you can get the integral surface to fix the problem, right? So here's an example that you have this blue area, and we want to actually put this area onto this blue area from a different image. And we do not copy the pixels, as we had mentioned before. We are replacing the gradients. So we will calculate the gradient of this image. We will calculate the gradient of this image, replace the gradient in this region, and then we solve something called a Poisson equation to do the integration. And the boundary conditions, the boundary pixel values on this boundary, they are required so that we can have the just like in 1D case, we were off by a constant. In the 2D case, to get the right results, we need all the pixel values along the boundary. For we get lucky here because we know the boundary conditions. It is the boundary pixels of the destination image where this patch is being replaced. So that's the theory, right? Now, Phil, have you shared the link to the GitHub repository where all the code is? Okay.
Yes, indeed, I have. Everybody should have access to that. If you're all joining us late, let me go ahead and drop that link again here in the Zoom chat. All right, everybody should have access to that now.
All right. So now let's let's go to the notebook. Just for the record, Phil and I had a debate on which notebook to use. I'm going to use this notebook because on Phil's suggestion, but we could have also used this other notebook I had, and Phil said that it's not good to... Well, the notebook is there in the GitHub repository if people want to try out, but we will actually go over this other notebook. All right, so this is an example of seamless cloning, and it's implemented using OpenCV. OpenCV actually has a bunch of computational photography routines or functions, and seamless cloning is one of them. There is also one for HDR, etc. So there are a whole bunch of very interesting.
There's some deblocking in there as well. A couple of other. How many? Somebody's going to ask this. So last time we checked, how many algorithms are in OpenCV total?
More than 2,500. If you
over 2,500,
all kinds of I mean, for even a single algorithm, there are many different implementations because it is optimized for the hardware. So if you're running on some Intel processor, it's going to look at the architecture of the processor and decide, okay, this is what the optimization should look like versus different architectures. Right? So it is there are a lot of algorithms in there. Right. So we have shared this seamless cloning notebook, and let's just go over the syntax of how this works. Now, the function is very simple. It says seamless clone. Then you have to provide the source, destination, mask, the center of the mask, which I actually don't like, but this was how it was implemented. So the center of the mask is a funny thing. I mean, we could have just said the left corner of the mask, but whoever implemented this, they chose the center of the mask, which creates an additional work for us. We have to actually specify, we have to actually find the center of the mass. Not difficult. Again, we'll use another OpenCV function, but I think it was not very necessary. So,
this is one of
the
the
other,
common problems in vision and in drawing graphics as well, is
yeah,
like, does it start from a corner? Does it start from the center?
yeah.
And is it cumulative from the center, or are the lengths of the sides still defined specifically? Things like this. Also, which direction is up? Is negative Y up, as it
Right.
is the case in so many game engines, but not all of them?
Right, right. Well, this one is even. Uh, I mean, I don't want to, criticize the person who implemented this, but this is even more complicated, because the center is actually not the center of the image; it is the center of the blob. Uh, the mask. Just imagine a mask. It is the center of mass of this mask. So that is not very obvious when you're coding it. I remember the first time I used seamless cloning, I did spend some time trying to figure out why my location is off, and I had to read the documentation very carefully to figure out what it is. Right? Usually, I think it is perfectly fine to read read the usage, but if you have to go and look at the documentation by looking at this, then that's not a good choice, right? That was made for that word center. So, and also, why even do the center of mass? I still don't know the answer why this choice was made. But
Like
anyways,
a lot of things, it could have been maybe they just had built it for a specific purpose, and kind of just ported it over without really changing anything.
yeah, and maybe there is some advantage that is not very obvious to me, that people found at that time. But anyways, it is the center of mass of the blob. So here we have this, we are setting up some standard imports, and then we are setting up matplotlib. And if this notebook basically would clone the repo for you, if you are using Google Colab, etc., then you can actually, this repo would be cloned for you, and you should be able to work on this. You can upload this to Google Colab and it will work. So now we read in the source image, which is the airplane, and the destination image, which is the sky. And we have just plotted these two images here. And now we find a mask. So here we are numerically generating the mask. We are just saying that we have this polygon, and you can see it is a very rough mask. We don't need an accurate mask to get this nice looking image, this nice looking output. We need a very rough mask around around this airplane. And then we create the source mask by using fill poly. So fill poly basically takes a polygon and fills it with whatever color you want in OpenCV. And this color is white. We are going to fill it with white. And as you can see that even though this mask is actually grayscale, we are using 3 channels for this mask. And the reason is that because it's going to be multiplied with color images, we want it to be a 3-channel mask, right? So that's one little detail you need to know. And these numbers are basically, you could have used a mouse to click on these points to get this very rough mask. And once you're done that, we need to, in this case, we have just fixed the center, that we want the center to be at a particular location. But I'll show in another notebook how you could have calculated the center of mass of this blob. So in this case, it doesn't matter a lot. We could just put where the blob center needs to go. So there are 2 kinds of cloning and seamless cloning implemented in OpenCV. One is called normal cloning, and other is called mixed cloning. So when you use this as normal cloning, you can put the image right here. So you can see that this image is right at this location, right? And I might have misspoken about what this center means. So this is my criticism about this choice of the word as well. So this, because even though I have used this many times, I still get confused what the center means. And I just misspoke what the center means. This center is actually the location in the destination image, in this sky image, where the center of this blob would land. Does that make sense? So
Yes.
the center of this blob, where it would land in this destination image, that's what the word center means in this. I really don't like this, but anyways, that's the implementation.
Somebody's gonna open up Git blame.
Well, you have to remember that many of these features are implemented. The core features are implemented by the OpenCV code team, but some of the algorithms which don't need a hardcore optimization, they are implemented as part of Google Summer of Code.
Mm-hmm.
And a lot of interns and external people are involved. The mentors are not OpenCV people necessarily. So some of this thing can slip in, but we still have to be very thankful for people who are contributing this.
You really are a tech CEO, Satya, blaming the interns and everything.
That's a
Thank you,
move,
interns. Thank you, interns.
Right. The interns are gone; they cannot defend themselves.
We do
Right.
appreciate them, though. Summer of Code is always a big help to OpenCV.
Oh, it is. Many features are implemented using that, and you'd be surprised how the quality of people who do these things.
Absolutely.
For example, one of the features that at one time I was the mentor, and this would be more relevant for people who are joining to India, they would understand. The person who, the intern who worked with me, he was JEE 5. So joint entrance exam is an exam in India where, 1 million people apply to this entrance exam for some engineering colleges in India, the Indian Institutes of Technology. And this guy was 5th in that, among million people. So very high quality people apply to the Google Summer of Code. And I encourage you to apply if you're a student and looking for an internship. Look for this internship announcement that comes out around in March or so for Google Summer of Code. Very good, program.
Yes, your contributions to OpenCV will outlast your time as a Google Summer of Code person, hopefully long enough that Satya and I can make fun of you.
That's true. All right. So there's another kind of cloning also called mixed cloning. Now here's this is an actual picture that this is a ticket. My older son used to create these little tickets which said, "I love you, Pa," right? But these are not, he did not distribute it, all the time. He was like 5 years old, but he had figured out somehow that you can actually modify behavior by rewarding people with tickets. So he would give out these tickets to me when I did something nice for him.
Satya's son, Pavlov.
Yeah. It's like you're treating me like a dog now, right? And I also realized that the dynamics has changed between kids and parents. Earlier kids used to look for, I want my parents'
validation.
approval,
Yeah,
right?
Yeah.
Now the parents are looking out for approval that, oh, I want to be a good parent. But anyways, so this is an "I love you" ticket I used to get from my son, and this is basically a gradient, texture, wooden texture, and we want to put this on this wooden texture. And the code is very similar, but there are two kinds of cloning. You could actually use normal clone or mixed clone. Those are the two options. And you can see that there is a slight difference between the two. If you use normal clone, there is a lot of blurring going on. And the reason is that in normal clone, all the gradients from this very plain area have been replaced. The boundary conditions are met, but in this region, it is actually taking the gradient from the I love you ticket, right? And in this mixed cloning area, it is taking gradients from both. It is basically taking the average gradient from both. So if you have a very plain background like this, it may make sense to use mixed cloning and not normal cloning, because otherwise you will get these pretty, pretty plain regions which you don't want. So mixed cloning produces a better I love you ticket. So that's the first set of applications we wanted to go over. I can take questions now, and then we will also show another application of it, which is blemish removal. The idea is that you click on a blemish and on a face, and it will be gone. I'll show that example. It's a Python code. But any questions people have with respect to this code?
Let's see here. It looks like, yeah, so we've got somebody asking, would there be any benefit to masking each word? Is that what's happening here?
Each word, no, you don't have to mask each word. Whatever texture you want to put in the destination image, you basically take a chunk of the source image and put it in the destination image. If you did not use mixed cloning, if you for some reason want to use normal cloning, then you could have masked each word and then put them separately. Yes, that would work. That would work very well.
Got it. Cool. Let's see here. Richard would like to know: is there a version of this that is all in C instead of Python?
I do have a version in C. I don't know whether we uploaded it to this. Actually, Phil, if you don't mind, could you search for GitHub?
Yeah, I'll take a look.
Learn OpenCV GitHub, and then seamless cloning on Learn OpenCV GitHub. There are examples in both C++ and Python. So the next piece is, let me show you a demo, and then I'll explain the code. So this is the demo for blemish removal. So the idea is that you click on the blemish, and it's gone. So you could see that there was a blemish right here. It's gone. Let's do this. We'll have to use a few clicks, and you can see that it is gone. Now, I actually want to take a question. I want to ask people, what would they do if they had a situation like this and they wanted to build an application? How would they use seamless cloning to remove blemishes? I mean, how would you do it in Photoshop? That's a good way to think about it.
Yeah, with Photoshop, you'd take your lasso tool, you'd go around there, or then maybe grab the clone tool from a clean part of the skin nearby.
So that's your answer. The idea would be that at the place where you're going to replace, you can assume that it is skin, right? So around that neighborhood, there could be other patches of skin that don't have blemish, right? And then you replace this blemish with that piece. And the only decision you need to make now is which patch to select, right? And you can select this patch based on the gradient information. You could say that I'm going to choose the smoothest patch among all the patches in the neighborhood. And then I'm going to replace that little patch over this using seamless cloning.
And it's important that those are nearby. You say in the neighborhood, you mean, close to the source, because otherwise, the lighting will be strange, the coloration will be different, and so it won't be as smooth of a patch.
Right. I mean, that's the assumption. It could land in the hair or something like that, right? I mean, the smoothness, the assumption is that we are sampling from the neighborhood, so it's very close to the original one, right?
Of course, in real life, you'd take your concealer and a Q-tip and dab it on there.
Right. So let's go over the code. So this is the code for blemish removal, and we can just quickly go over the code. So here, it finds the best square. So it finds the best So we don't even need to go a circular, because we are using seamless cloning. We can just look for square patches. When you click, let me show you the radius. So when you click, I think we are taking about 15 by 15 patches, or maybe 30 by 30 patches, and creating a square region around it. So we have a width of 2 times square. So whenever you click on the image, it is taking 30 by 30 patches around that region, and it wants to replace that patch using seamless cloning. And here we have this function called find best square. To find the best square, we are going in. If you look carefully, look at the code carefully, what it is doing, it is going in a circular fashion around the original square. You can see that we are adding the square width and the square height. So it is going one step outside, and it is going around that region in a circular fashion. And wherever we are basically looking at the gradient, we are looking at Sobel operator in OpenCV finds the X and Y gradient, which is, where in a smooth texture, there is no gradient. The gradient value would be 0 if you have a perfectly white or perfectly solid colored region. But if there is a line or an edge, you will see a sharp change in gradient, because gradient is nothing but derivative. It responds to sharp changes in intensity values. So we get this X and Y gradient values. And based on that, if it is less than some minimum value, we say that it is one of the options for, for replacing. And then we choose just based on this very simple criteria. And the rest of the thing should be pretty straightforward for you. You can go and look at the code. We are simply replacing that region. We are finding a smooth region. Here you can see, find best square. We are finding a smooth region. And then, we are actually masking the square. We are actually using a circular mask, but it is strictly not required. So we create a circular mask and then use this smooth region and put it in the source image. So pretty simple, right?
And you'll notice if you look at the code too that, as is fairly common, the click handling code is longer than the computer vision code in this example. It's
right.
Interfaces are hard, folks. Interfaces are hard.
Right. So that's how you would do blemish removal. You can see that, it's pretty straightforward. Some of these things that look magical from the outside, especially if you have not used libraries like as powerful as OpenCV, then it looks very difficult. But with very simple functions, here we have just used 2 different functions. One is seamless clone, and then we used Sobel operator to find regions with a high amount of gradient. So the last thing I want to show is actually that notebook. I want to show a video from our course video. In this video, we are going to describe a fun application of seamless cloning. We are going to blend President Obama's face onto President Trump's face in this application called face blending. Let's see how it is done. Here we have our standard inputs. We're going to create a monster, folks. We are setting up matplotlib. And then we read in the image of President Trump as the destination image. We read in the image of President Obama as the source image, and we read in the mask. Now, we have explicitly asked the mask to be read as a color image because we want the mask to be applied to all 3 color channels. Now, in this line of code, we are simply displaying the 3 images we have just read. Now, what happens if you try to alpha blend this image using this mask onto that image? Let's see what happens. So here we have an alpha mask. We simply create a copy of the source image, and we divide it by 255 we convert it to floating point and then divide it by 255. So the values inside alpha go from 0 to 1. And then we can simply do an alpha blend. So the source image, which is President Obama's face, gets multiplied by the alpha mask.
Sounds like you're trying to sell us something at an auction here.
Image
the
gets
sped up Satya voice is throwing me for a loop.
And then we add the 2 images together to get this final image. Of course, this looks horrible because the lighting is not right. And this just doesn't look right. So what can we do to fix it? Of course, you have guessed the answer. We need to do seamless cloning.
But before we do that, we need to find the center of the mask, because in seamless cloning, as it is implemented in OpenCV, we need to pass in the center of the mask where it should be positioned in the final image. So we calculate the center of the mask using image moments, as we had done before a few weeks back. So we threshold the image and convert it to binary. As you know that the source mask was a 3-channel image, we just need one of the channels. So we pick the first channel and threshold it to get the binary mask. Once we have the binary mask, we calculate the moments on this binary mask. And using moments, this is the standard way to calculate the center of the mask. Once we have the center of the mask, we are going to pass it in the seamless clone function along with the source image, the destination image, the source mask, and we are going to use normal cloning to get the final output. As you can expect, this was the source image, this is the destination image, and using normal blending or alpha blending, this is the result we get. However, if we use seamless cloning, this is the result we get. Although the image may be disturbing, qualitatively, it is so much better than this image.
Very disturbing.
Of course, politically,
kind of looks like a motivational speaker, like a Tony Robbins.
That's all we want to
look
cover
like Tony
in this
Robbins?
Video. See you in the next video.
That guy's voice sounds crazy, I bet. The Trump-Obama there is...
That is it. That's the thing that I wanted to show. And the coupon code for the course, if people are interested, they may have missed the July 4th. I think it's a 20% coupon code. It is OpenCV-webinar. And I think there are only 5. No, I'm pretty certain that there are just 5 available right now. So you can go and check it out for people who want to, learn these kinds of techniques. This specific example was from Computer Vision 1, but this kind of techniques and these kinds of code is in all our courses based on what you're interested in. So let's ask some questions. What questions?
Yeah, so we've got time for questions still. If you've got questions, go ahead and put them in the Zoom chat or send them as a comment wherever you're watching us. Before we get to questions, though, we'll do our giveaway of OpenCV course of your choosing. If you want to follow along the tutorial you saw here today, you'd choose Computer Vision 1, as Satya just said. So during the presentation here, we mentioned the names of a couple luminaries in computer vision, algorithm and equation writers par excellence, specifically 2 people. What were their last names? The 2 last names of the computer vision mathematics, of the mathematics pioneers that we mentioned on the show. Patrick says intern 1 and intern 2. That is incorrect, but I send me an email. We'll get you something. That's a good answer. I've got stickers. You want some OpenCV stickers? We'll put something in the mail for you, Patrick. But yeah, so the rest of you, the 2 mathematicians that we mentioned here during the episode, I finally stumped them. It took 67 episodes. I got him. All right. Oh, you're close. Donna's close. I don't believe we mentioned the second one. Yeah, I might be wrong.
So is the question about the scientist whose name after which the editing is?
There were 2, yes.
And the boundary condition? Should I?
I believe so. Yes.
Okay.
Donna is half right here. If you look in the chat, you'll see Donna is half right. We specifically said their names during the show. Oh, man. Hey, Max. You got it. Thank you, Max. The answer was Poisson and Sobel. So congratulations, Max. Please send one email to phil@opencv.org, and I will make sure that you get the course of your choosing. If you already know what course you want, go ahead and put that in the email, and we'll pass it along to the courses team, and you can get started right away. All right, let's get to questions here. Patrick would like to know, to do this kind of blending, he says he's read about using an autoencoder or decoder. So is seamless cloning a sort of primitive method of autoencoding, or is that incorrect?
Yeah, so the difference is that, there is no training involved. So you don't need any pre-trained models, nothing. You don't need any kind of training to pull this off, right? And it's also very fast, right? So, but let's say there was a very specific kind of cloning you wanted, right? Let's say then you could end up using GANs and things like that, where let's say you want to do face replacement for a video, right? Then I would not suggest this one because it would not be consistent. From frame to frame, the Obama Trump blend would not be consistent. And so you would not use this technique. You would use something based on GANs, which will make the video frames consistent. So this one, the beauty of this thing is that it doesn't require any training. It will work pretty much on any image, right? You will get reasonable results for a wide variety of problems, and it works out of the box, right? One line of code.
I think you've Patrick's question and your answer actually gave me what I think is a pretty good idea. We should have a contest. We should have people send us the funniest blends. Like send us the funniest gradient blends. We'll look at some of them on next week's show. Send those to phil@opencv.org if you make something.
What's the
using
prize? We always give prize.
We'll have to. Hey, I mean, you'll have to tune in next week to find out what the prize is.
All right.
Yes, and flattery will get you everywhere. If my face is in it, you're way more likely to win. We'll just get that.
That's awesome.
Get out in front of that one. Yes, we'll also provide some photos of the shop cat if you want to work the cat in there. Stay tuned to the @OpenCV Weekly on Twitter account. We'll post there. Akshay would like to know, would seamless cloning not work effectively when the object we're trying to clone is relatively bigger compared to the target image? For example, the airplane was very small compared to the background, but in the face blending, the face is the largest part of the image, not the blemish, right?
Right. So it actually doesn't matter as long as you can shrink the image. Let's say the airplane was very big and the sky was small. You have to actually shrink the image before you do seamless cloning, because seamless cloning is not going to shrink the image for you. You have to do that pre-processing, and then you pass it on to seamless cloning and tell it where you want the thing to go, right? And the only other thing to keep in mind is that, like you said, like we saw in the Obama notebook, we need to find the center. When we are doing something like a face and we want the exact location where this thing should go, then we need to find the center of mass of the mask as well to make sure that we place it correctly.
I think that makes sense. Thanks for the question, Akshay, I believe. Jason doesn't have a question, but Jason says he would use this to add hair on his head instead of removing blemishes. I think a lot of people can identify with that one, Jason. You're not alone. That's about all we got for questions right now. If you all want to shoot some right now, we can ask, and we'll be the top of the pile.
And feel free to tell us if these kinds of tutorials are useful. We can work more of them into our webinars, because it's without feedback we don't know whether people's expectation are that they'll be getting these tutorials, and if they like it, then we can do more of these tutorials for sure.
Yeah, and we can definitely go. You can go by how many people are watching, but that's not necessarily the right measurement for if these episodes are good or not. So yeah, please your feedback and suggestions, please to newsletter@opencv.org. Yeah, we're next week we've got our friends from OpenVino will be back talking about ONNX and OpenVino. We should be back in the fabulous OpenCV weekly webinar virtual set created by Light Twist with our as of yet unnamed cat friend. Please send those suggestions also to newsletter@opencv.org. Satya, you want to take us home?
Yes, thank you so much for tuning in today. And I really apologize that we could not do the original webinar that we had planned for, but that's coming soon. And thank you, Phil, so much, because you are the one who puts together these shows. I really appreciate your effort, and we'll be back next week.
That's right. Thanks everybody for watching so much. We will be back next week, same bat time, same bat channel, 9 a.m. Pacific, wherever fine video webinars are found. Take care of yourselves out there. Take care of somebody else if you can. We'll see you next week. Thanks so much for watching this episode of the webinar. Please hit that like button, subscribe, and don't forget to tap the little bell icon to be notified when new episodes drop. This week's episode was brought to you by OpenCV Courses. Learn computer vision and AI from the best at opencv.org/courses. If you'd like to be in the audience next week, subscribe to the OpenCV newsletter.